Okay, here we are, and we're marching through this mini unit on quantum physics. And now we're going to turn our attention to the Bohr atom. Because one of the observations that we saw before was that, hey, whenever we have these continuous spectrums, whenever we look at the spectra of elements, so here, say, is hydrogen, here is the spectra of helium, here's the spectra of mercury. Whenever we look through these spectrums, we see these lines, these discrete um, wavelengths of light that are emitted. And so in lesson one, we learned that any object, when it's heated, gives off this continuous spectrum of infrared through visible all the way to ultraviolet. Okay? But something very, very different happens when we isolate one type of atom. So if we isolate one type of atom in gas form and we run a current through it, rather than a continuous spectrum, we obtain a line spectrum. And basically, it only shows certain colors or at very specific wavelengths of light. So this would be what hydrogen would show. It would be this right here. This would be hydrogen's line spectrum. And this is one of the ways that we can determine what things are composed of, because elements will have very, very different line spectra. They're, of course, all very unique. And so you can see that from the various spectra that really elements only just that all their spectras are very, very different, right? So in the late 1800s, scientists gathered tons of data on this. And this in 1885, this is a little bit interesting. A Swiss high school teacher named Johann Jacob Balmer found an equation that correctly predicted the 4 visible emission lines of hydrogen. So this right here is Balmer's equation for hydrogen. And it's that 1 over the wavelength is equal to 1.097 times 10 to the negative 7 over 1 over 2 squared minus 1 over n squared. And so this is what's important, right? Because he predicted this, what's called empirically. So he used observation to describe what he saw. So there is no theoretical basis for this equation yet. He did this just by observation. He was able to come up with this equation that predicted the wavelength of each of those lines. And so a couple other people did that too, right? The Paschen series, which was in the infrared section of the spectrum, the Lyman series, which extended into the ultraviolet range. Basically, because of Balmer's discovery, other spectral lines were found in different ranges of the electromagnetic spectrum. And so it's important to note that all of this work is empirical, which is there was no theoretical basis. So the scientific community just used them, not really knowing why. And one of those things was that basically we're bothered by the classical treatment of the atom. So enter Bohr and his quantum model of the atom, because all this stuff was happening, and these quantum models were trying to be used to explain, peak wavelengths and all of these things. But these were the two main ideas. Their model of the atom at the present time was that it didn't explain these atomic spectra at all. So why do atoms give off only certain spectral lines? Like, it didn't explain that. Our classical model of the atom, or the model of the atom at the current time, couldn't explain this. Why do atoms only absorb the wavelengths that they emit? So that was another big question. And especially the stability of the atom. If the electron's moving in an orbit around the nucleus, it's accelerating. So think about that. Uniform circular motion. Why doesn't it lose energy and eventually spiral into the nucleus? Like, they were really bothered by this, and so they should have been. So Niels Bohr, Danish scientist, introduced this new model of the hydrogen atom. And in grade 12, we're going to restrict our discussion of the atom to the hydrogen atom. There is, of course, more models of course, all the elements, but we're going to restrict our discussion to the hydrogen atom. So based on Rutherford's planetary model, right, that explained, basically Niels Bohr was able to introduce one that did explain the spectral lines. So Bohr's model included some aspects of classical physics, it included a little bit of Planck's work, it includes some of Einstein's work, and it included some of the earlier models of the atoms. So here was I'm going to show you the basic ideas of Bohr's model. Here's what they are. The electron moves in circular orbits around the nucleus under the influence of the Coulomb force of attraction. Fair enough. That was one basic idea. Okay, so at the time, that was one basic idea. Of course, we've even moved a little bit past this now, and you've probably learned that in chemistry, but this is what he had proposed. Second, only certain electron orbits are stable. These stable orbits are the ones where the electrons do not emit radiation. Okay, so there's certain stable orbits, and in those stable orbits, there's no radiation. Third, radiation is emitted by the atom when the electron jumps from a more energetic initial orbit to a lower energy orbit. So whenever the electron jumps from a high energy state to a low energy state, this is part of Planck's contribution, or this is where Bohr kind of used some of Planck's work. This happened. And finally, the size of the allowed electron orbits are determined by a condition imposed on the electron's orbital angular momentum. So basically, the angular momentum is quantized as well. So we know that linear momentum, quantized energy, quantized angular momentum, quantized as well. Okay, so to investigate these are the basic ideas. Okay, basic ideas. To investigate these, let's look at the conservation of energy, and then we're also going to look at the conservation of angular momentum. Even though in grade 12 you haven't learned about what angular momentum is yet, we're going to talk about it in a hand-waving kind of way. All right, so let's look at the conservation of energy first. An electron orbiting a nucleus has two kinds of energy. It has kinetic energy because it's moving, and it has potential energy, which is negative because it's in a potential energy well. Okay, so an electron orbiting a nucleus has these two types of energy. It's moving, so it's got kinetic, but it's got this Coulomb force of attraction keeping it in place in the orbit. So the energy of this electron, we can combine these two things, and here it is. The energy of this electron is 1/2 mv squared minus k e squared over r. Okay. So we can also look at centripetal force, right? Because the centripetal force is caused by the Coulomb force of attraction, which is k e squared over r squared. And so mv squared equals k e squared over r. Because centripetal force is mv squared over r, as you know. And so we can basically massage this and pop this into here, and we can arrive at a general expression for the total energy of electrons using really nothing other than what we've talked about before. So here it is right here. Okay, so here it is. The energy of this electron in an orbit is equal to k e squared over 2r minus k e squared over r. And we can simplify this quite nicely by saying that the energy of this electron in orbit is minus k e squared over 2r. And there it is. We're going to call this equation number 1. Okay. Now let's look at the conservation of angular momentum. So some of this you're going to have to take basically because I say so, and you're going to have to trust me on it. But similar to the momentum of an object traveling in a straight line, we can also describe the momentum of an object as it's rotating, and we call that angular momentum. So L is the symbol that we give to angular momentum, and of course here we'd have the mass m and a velocity v rotating with a radius of r. Okay, so Bohr assumed that angular momentum could be quantized because of its relationship to energy. So when we looked at momentum and we looked at energy, we were able to come up with this very handy relationship between momentum and energy, because they are related in a lot of ways. In order to quantize angular momentum, we need to quantize both velocity and radius. So here we can modify this expression above. We don't quantize mass, because mass can be anything, but velocity is quantized, radius is quantized, and that is what quantizes angular momentum. All right. So here n is a positive integer that represents the energy level of an atom, just like what Planck said. So Bohr also suggested that the smallest possible value for L, for the angular momentum, was h over 2. So he suggested that. So here is what we get. We get that Ln, the quantized angular momentum, is equal to n h bar. And h bar happens to be just another constant. We can talk about that in a minute. H bar is really just h over 2 pi. So if I rearrange this little equation right here, I get this value for velocity, which is nh bar over m times rn, right? Which gives us the quantization of the velocity. So now if we substitute this into our equation for centripetal force, because I have velocity in here, and I substitute this value in, because this is still the electron that's going around, then I get this really ugly looking expression. It can be simplified. And that's that the radius of the hydrogen atom is equal to h bar squared times n squared, all over me/ke squared. We're going to call this equation number 2. So this final expression for r is the theoretical radius of the orbit of an electron in meters, where n is some quantum number. Okay? So the one thing you have to understand about this is that all of these things, the mass of the electron, k, e, h bar, all of these things are constants. All of these things are constants. Right? And so really, if we multiply all those constants together, this is what we get. The radius at a certain energy level n is equal to 5.29 times 10 to the minus 11 times n squared. Right? So all this simplifies down very, very nicely. So here's what we have. Here's an example. Because all of this derivation, now we kind of need an example. So what are the energy levels and radius for an electron in a hydrogen atom in the 4th energy level? All right. Well, let's look at equation number 1. Equation number 1 is that the energy level at a certain level, at a certain quantum state, En, is equal to minus ke squared over 2rn. So that's equation number 1. Here's equation number 2 that we derived, is that the radius is equal to h bar squared n squared over me/ke squared. So if I want to get rid of this Rn, right, I can combine it with this right here. And here's another equation that I can put a box around. Is that En, the quantized energy in this hydrogen atom, is equal to minus 2.18 times 10 to the negative 18 all over n squared. So now, I've got energy that depends on n, and I've got radius that depends on n, and so I can find the energy and the radius for an electron in the 4th energy level because n is equal to 4. So E4 is equal to minus 2.18 times 10 to the minus 18, all divided by 4 squared, and I get this value of negative 1.36 times 10 to the negative 19 joules, which means that if an electron is in the 4th energy level in the hydrogen atom, this is how much energy it would require to knock it out. And what's the radius of this? Well, I've got 5.29 times 10 to the negative 11 times n squared, which means I make the substitution for n, and I find 8.46 times 10 to the negative 10 meters. So this is the radius, the approximate radius of the hydrogen atom in the 4th energy state. So these things are really, really helpful because now we can start talking about photon wavelength. So based on the discoveries above, we can now determine the wavelength and the corresponding energy of the photons that escape when electrons jump from one energy level to another. And so this is what provides the characteristic spectrum that we observe in gas discharge tubes. So we again look to the conservation of energy. All right, so energy initial minus energy final is equal to this photon wavelength. right? Or the energy that this electron has initially minus the energy that the electron has finally equals hc over lambda. So this right here is a very meaningful and straightforward way to find the wavelength of a photon that's emitted when an electron jumps down an energy level. So let's take a look at how we're going to use this one, because we have all the pieces now. An energy in an electron in a hydrogen, an electron in a hydrogen atom makes a transition from n equals 2 to n equals 1. So it goes from a high energy state, n equals 2, to the ground state, n equals 1. Find the wavelength and the frequency of the emitted photon. Okay, so here's what we know. N equals 2, n equals 1. So what we need to determine is we need to determine the difference in these energy levels. So I've got EI initial minus EI, or E final, EE final. But I have an expression that I just derived that's going to tell me, oh, this is the energy in that state. Now, be very mindful. These negatives are in here, and they're very important. So be very mindful of the negative signs. Because what I get is I get a positive number if I'm careful of these negative signs. And I divide by Planck's constant. And I end up with a frequency of 2.46 times 10 to the 15 hertz. And if I just use V equals F lambda, I can make a very quick calculation. And I can determine that this is 121 nanometers. So when the hydrogen atom makes a transition from n equals 2 to n equals 1, this is the wavelength of the photon that is released. Okay? And this is basically how the Bohr atom explained the hydrogen spectra. What we've seen over the past couple of lessons is this notion that sometimes we treat photons like waves, and sometimes we treat photons like particles. And so light is a very strange subject matter, right? So it has properties of both of these things. And so really what it comes down to is that we can't say that light is this or it's this, but rather that it's both. And this is known as the wave-particle duality of light. So Bohr suggested that basically to understand any given experiment, we must either use the wave or the photon theory of light, but not both. But to fully understand light, we need to be aware of both models. And this is the principle of complementarity. And so when we look at individual experiments, we use one or the other, not both. But to truly understand the subject, we need to be aware of both things. And that's kind of the end of lesson number 3. Lesson number 4 is about Heisenberg and his uncertainty principle.